and welcome to chapter 19. This is about weather, and weather's not really my thing. I'm not a meteorologist at all. I've never taken a meteorology class. Science of studying the atmosphere, it's just not my background, not my knowledge set. So I also haven't spent a lot of time studying this chapter. As you know, I've been coming home from traveling, and I wasn't going to do a lecture at all, but I thought, well, I'm going to do something this morning just in terms of giving you tips on how to study and how to prepare for an exam. So I'm going to be talking about the subject, but I'm also going to be talking about how would I approach the subject as I'm preparing for an exam. And I realize this is last minute because you have an exam at 5 o'clock today, and it's 6 o'clock or 5:30 in the morning or something. It's early. I got up early. Okay, so weather's a big deal. It determines a lot. It affects everything, right? So what we wear, where we go, when we do our activities, even what our mood is. And we tend to like the weather from the area we grew up in. Our bodies tend to get used to a certain pattern, and then when we change to something really different, we may or may not like it. So if you grew up in Alaska and then you move to Arizona, chances are you'll miss Alaska. But on the other hand, people get tired of weather and they like to have a change. So if you grew up in South Texas and you get tired of heat and humidity or something, then I don't know, you like to go someplace maybe with 4 seasons and snow, or anyhow. Come on, move. Okay, so when we talk about weather, what are we talking about? Well, usually, when you get the weather report, what do they give you? They're going to give you the temperature, the high and the low for the day, the predicted high and low, how hot or cold is it right now, the humidity sometimes, whether it's going to rain or not, or snow, sleet, hail, whatever, some sort of precipitation, if it's going to be windy, where the wind is coming from, how fast, how cloudy it is, and maybe the types of clouds, and how many. You could, in your weather report, you might also get something about the air quality. So usually, you look at the weather forecast, and let's see, let's do a weather forecast, right? Weather.com, Del Rio, Texas. And what are we going to get? Confusion. 77 degrees. Feels like 77. Now that feels like, that's, so the weather, the temperature may be one thing and it might feel like another. That takes into account the wind and the humidity, which can affect your sensation of the temperature. So if it's cold and windy, it's going to feel colder than it actually is. If it's cold, windy, and humid, it's going to feel colder still. So we just get a little, we have a weather radar map, which is nice. We see nearby rain, and we can get something, people often like the 10-day forecast if they're going to go do something. And just, it just gives us the quick, how cloudy it's going to be, highs and lows, which doesn't look too pleasant. Chance of precipitation. Today's the last day for the next while. Yep, next 10 days. Wind, the direction of the wind, where it's coming from, the direction the wind's coming from, and the miles per hour, and the humidity levels. So there we have it. And let's just compare that to where I was. I was vacationing in St. George, Utah, which is southern Utah, and people in Utah, they don't want to be in St. George this time of year because it's hot. So let's look at how it compares on the 10-day forecast. 110, 105, 105, 104. Definitely hotter. But if you look at the humidity, 11%, 18%, 20%, 33% is their highest day. but they have some days 11%. And that will make a pretty big difference. So if I go back to Del Rio 10-day forecast, having humidity 40, 50%, 60%, definitely you can't cool off as well through sweating. So do you like a dry heat? Do you like, not quite as hot, but more humid? Anyway, back to the PowerPoint. So, biometeorology. Meteorology is study of weather. Biometeorology, study of how weather affects living things. This isn't like a big field of study. I've never personally met a biometeorologist, but looking at how weather affects living things, living systems, and this is going to be relevant for if somebody wants to predict, mosquito. Somebody wants to predict cotton yields based on the weather patterns, or how cows are going to do in a certain area, or how weather might affect the spread of malaria or the numbers of mosquitoes, right? These things, weather has an impact on these things. So if you're interested in weather and living systems, then biometeorology might be for you. Now, tip, turn everything into a question when you study. Okay, so instead of just reading biometeorology, blah, 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 ask yourself, what is biometeorology? And without looking at the slide, trying to turn around and say, okay, biometeorology is this, the study of how weather affects living things, and give some examples. Turn everything into a question. Greenhouse effect. What is the greenhouse effect? Well, without looking at the slide, greenhouse effect, basically more heat coming in than what goes out. Okay? Look at a greenhouse. Look at your car in the summertime. Well, any time of year. Any time of year, your car is sitting out in the sun. It's going to be warmer inside your car than outside. Why? Why is that? Because the radiation coming in is short waves and passes through the air, through glass, without really doing much. I mean, it's passed clear across space, and it didn't do much. It just kept going, straight, going. So it passes through the air, passes through the glass, hits the surface of the car inside, and warms it up. That radiates some of the heat back out. But the radiation is longer waves. And the longer waves, here's the window. Okay, the longer waves hit that and tend to bounce off. So the radiation, the heat, the warmth that's radiating out, tends to stay in. It bounces off the glass and doesn't pass through it. So the short waves coming in pass through easily. The long waves, they don't pass through as easily. So you warm up, right? That's all that's happening. Same thing with the whole planet. These short wave radiation coming in comes through the clouds, through the sky, and hits the planet, warms things up. The heat, the energy does radiate back out into space. And we do lose, it eventually does go back into space. But it tends to bounce off of clouds and bounce off of things in the atmosphere, just even the air molecules, and stays in, right? And some gases, like carbon dioxide, is a greenhouse gas. It's just that radiation is more likely to bounce off of it and stay in for a little bit longer. So, it can warm things up. Methane is probably a stronger greenhouse gas than carbon dioxide. We talk a lot about carbon dioxide because we're releasing so much by burning, gasoline, oil. But methane, we're also having a significant impact by the number of cows that we have on the planet. Methane is made by the bacteria inside the cow's guts. Basically, cow flatulence is having an impact on global climate. I still haven't gotten that mosquito. Anyway, so factors affecting Earth's temperature. Turn it into a question. What things affect the temperature of the Earth at any one point? Why is Del Rio a certain temperature? Let's compare it to where My sister lives in Bellingham, Washington. Okay, so let's look at her 10-day forecast really quickly. 78, 77, 69, 68. These are the highs. Okay, and the lows in the 50s. Sunny, partly cloudy. 85% humidity, 63, 65. Cool and humid. Okay, pretty high humidity. Much, much cooler. So why is that? Okay, what affects that? And so here's one thing that affects it. Okay, there are many things that affect it. So let's compare, Del Rio, Texas, to Bellingham, Washington. What are some of the big differences? One is the curvature of the Earth, and this basically gets at how far away from the equator you are. My sister is further from the equator, right? She's further up, and so the sun's rays are not hitting as directly. The further north you go, the more indirect the rays of the sun are hitting. Okay, so there's 2.5 times more energy hitting in the equatorial region than at the poles. Okay, that's just how things are. Because the sun's very, very, very far away, the rays are coming straight, and the Earth is curved. So this shows it just fine. Okay, so curvature of the Earth, that's one effect. The further you get from the poles, the less solar energy is hitting. So if you're going to decide where to put a solar power plant in this country, Minnesota is not going to be as good a place as Texas, and Arizona, might be better still because they have fewer clouds. The tilt of the Earth, and this has to do with the last slide, the curvature of the Earth, but the fact that the Earth is tilted relative to its axis. It's rotating, but it's not sitting up like this rotating. So one rotation equals a day, and so the rotation, the spin, is that even, that's not even necessarily shown. Kind of a big deal that the Earth is turning, right? Because you're always having, it's either sunny or it's dark. Okay, so part of the planet's always in the light, part of it's always in the dark, and the whole thing's turning. And that's our perception that the sun is moving. Of course, the sun is staying still, and the Earth is turning, so our view of the sun, it looks like it's going across the sky. Obviously, that affects the temperature. There's about a 20-degree difference right now between daytime and nighttime. And because it's tilted, this is going to give us seasons. Because what do we do in 1 year? We make a trip all the way around the sun. Right? Here's the sun, so we're spinning. We spin 365 times for every one time around the whole sun. So every birthday I like to tell people, good job making it, on another trip through space around the sun. That's a big trip. I'm not going to look it up right now, but how far do you travel in 1 year? How far does the Earth travel in 1 year around the sun? That's how far you and everybody else traveled from one birthday to the next. Okay, but because it's tilted, this means that in what we call summertime, the northern hemisphere is getting more sun, and the southern hemisphere is getting less sun. And it's still getting day and night, but look, if you're at the South Pole, the sun never shines right now. Right now is not the time to visit the South Pole. You want to go see penguins, wait until January, because in January it will be the opposite. It will be sunny all the time down in the South Pole, because the Earth will be clear over here. Right now the Earth's over here in terms of where it is relative to the sun. And again, the sun's very far away, but this is as good a picture as we're going to get. So right now the South Pole looks like this, always dark. And North Pole it's always light. The sun does not set. And that's a really weird thing. I visited Alaska once in the summertime. Well, I've only visited Alaska once, but it was middle of summer. And at 2 o'clock in the morning, the kids are outside playing and everybody's awake and doing stuff because it's daytime. It's always daytime. And people don't have any real schedule because the sun never goes down. So what are you going to do? You just sleep now and then when you feel like it, but there's no particular time to sleep. Conversely, wintertime, dark all the time, you never see the sun. It almost gets light, but not quite. Or, just again, it depends on how far north you are. Southern Alaska, you'll see the sun a little bit. It'll go just barely across the horizon. But big deal. Seasons are a big deal. And there's seasonal affective disorder, SAD. So people like my sister up in Washington, they have to be a little careful because in the wintertime they're going to have such short days because of how far north they are that the not seeing the sun, it has an effect on people. It is depressing if you just never see the sun month after month. Okay, so we just passed summer solstice. What was it, June 21st, 22nd? So the longest day of the year, but it's the shortest day of the year for the southern hemisphere. So in Australia, this is winter solstice right now, but we called it summer solstice because we're up north. Okay, the clouds, that's going to affect temperature. Now, we get a fair number of clouds here. Compared to Washington, not as many. Eastern Washington, Western Washington, where my sister is, they're next to the ocean. They get a lot of cloud cover. Clouds tend to, make it a little cooler in the daytime, but actually a little warmer at night because the radiation escapes better. Those long wave radiation escapes better when there are no clouds than when there are clouds. So this is, if it's cooling down, this is wintertime apparently, cooling down to 25 degrees at night on a clear day, it might only cool to 45 degrees if there's heavy cloud cover. Now, it's going to have a harder time warming up during the daytime with cloud cover, but cools down less at night. So you'll have less between the hottest and the coldest. It's going to be less difference. If you're talking about high desert, say in Utah, with very low clouds, the daytime high and the nighttime low, maybe it's going to be 30 degrees difference instead of 20 degrees difference. Summer days versus winter nights. We talked about seasons, right? That in the summertime you're getting more solar radiation, the days are longer. So why is it hotter in summer? Well, you see more sun. The days are longer. The angle, because of the tilt of the planet, you're getting more sunlight. Period. Winter, less time seeing the sun. The days. This planet's not changing how fast it's spinning. Right? That's not it. It's just that because things are tilted. Unless you're at the equator, day and night are not going to be equal most times of the year. So here's summertime. If you're at the equator, it's 12 hours day, 12 hours night. The further you are from the equator, the bigger the difference between day and night. So here we have, longer nights, shorter days. It's wintertime down south. Here we have longer days, shorter nights. I mean, it's still half and half, but the Earth's tilted, so it's not half and half. Anyhow, so summer, longer days. Latent heat of land versus water. Okay, so this is a good comparison between Bellingham, Washington, and Del Rio, Texas. Bellingham is next to the ocean. The ocean doesn't change temperature as quickly as the land. Okay, the water water resists changing temperature. Think of it this way. If you heat up a pan on your stovetop and you heat up a pan with water in it, I mean, it just takes a lot more energy to heat the water. It resists change, and it has to do with the hydrogen bonds of water. But anyway, the more water you have, the more the temperature is not swinging as much. Okay, big body of water, it's going to resist heating up, so it heats up slower and it cools down slower. So no water at all, far away from water, you're going to have this much temperature swing. Right next to water, you're going to have, this much. So big swing, little swing, and that happens in the wintertime too. Okay, if you're next to the water, you're just not going to change temperature as much. So San Diego, California, it's almost the same temperature year round. Bellingham, Washington, they're just not going to get really, really cold compared to if you stay even with Bellingham and you go directly across, you're going to hit someplace in Montana, and I promise it's going to be much, much colder in Montana, far from the ocean, than it is in Bellingham, next to the ocean. Winds. Okay, this is changing temperature based on convection. Okay, we talked about radiation. Convection is the wind currents, the moving air changes temperature. I love how drastic it is here in South Texas, where we get, in the wintertime, one day we're getting winds from the north and it's cold, and another day the winds are more from the south and it's warm. And so we're getting the weather from far away pushed onto us. So the temperature will drop really low one day, and then boom, it's back up much higher. So that's fun. It's always the cold air pushing, okay, and the cold air is more dense. When you cool a gas, the molecules are moving slower, and so they're closer together. So you have more molecules per amount of area. This more dense gas is heavier, and it puts more pressure. So a high pressure system is coming from colder air pushing down, and it pushes under the warm air because the warm air is less dense. And anyway, let me just show you the place that we lived for 15 years is Cache Valley, Utah. It's a beautiful place, but the inversion can be pretty bad. So here you can see a pretty distinct line between the cold air that sits in this valley and the warmer air above, and this can just be a soup, right? It's not a cloudy day. You can see it's perfectly clear, but this is just all the pollution and the muck sitting in the valley, and it can stay there for weeks at a time. The air quality can actually get really terrible. So here it is, this little town in the mountains, and you think, oh, beautiful and so clean and pretty, but it's surrounded by mountains, and the cold air settles in there and stays. And so you just have this mass of cold air, and it creates blah, right? So we lived here for 15 years, loved it, but I hated that the air quality was terrible. Here it is, very few clouds in the sky, but boom, this valley filled with smoggy air. So anyway, I do like that there's no inversion here. But we do have a lot more wind. Okay, without the mountains, we have a lot more wind here, and that can change the temperature quite drastically. Altitude, low altitude versus higher altitude. Bellingham, Washington is basically sea level. Here we're at about 1,000 feet. That's not a big difference. The place I just showed you, Logan, Utah, that's 6,000 feet in elevation, or 5,000, 6,000. So that's making a difference. Basically, as you go up higher and higher elevation, it's going to get colder and colder. And there's just no way around that. Why would this be? Why would it be colder at a higher elevation? Because you say, hey, I'm closer to the sun, right? Well, not really. You're not any closer to the sun, really. But you have, because the sun's so far away, but you do have less atmosphere between you and the sun. So you are getting a lot of solar radiation at these high altitudes. But remember that Earth's gravity affects everything that has mass, and gas molecules have mass. So the gas tends to sink down. Oxygen, carbon dioxide, nitrogen. Most of the atmosphere, remember, is close to the planet. And the further up you get, the less atmosphere you have, the less gas molecules. So, how does that affect temperature? I think there's just less atmosphere to keep the radiation in, right? The long wave radiation bouncing back off at a high altitude. I think you just lose it to the out into space faster. I think that's why things don't heat up as much at the high altitudes. So it's about 3 degrees Fahrenheit for every 1,000 feet in elevation. If you're going up in a balloon, it's going to get really, really cold if you go up high. Like crazy guy who jumped off 25 miles up, he needed a climate-controlled spacesuit because it's going to get super, super cold. The air is super cold, but he is getting more and more solar radiation because he doesn't have the atmosphere to filter it out. And so he actually, because he had a spacesuit that would absorb that radiation, he was at risk of overheating when he was up high, oddly enough. Okay, even though the air was cold, his suit was taking in the heat. Higher you are, the colder it's going to be. That's going to have an effect. So this is Mount Kilimanjaro in Africa. African savanna, it's hot, it's summertime, definitely hot, but here, Mount Kilimanjaro, it's highest point in Africa, and there's always snow up there because it's almost 20,000 feet in elevation. I think it's about 19,000 something. It's high, right? 20,000 feet. You can see that it's always, well, in this example, 90 degrees at sea level, 30 degrees at 20,000 feet. So that's freezing cold, and it's always going to be freezing cold. This is one of the easiest hikes of a highest mountain peak. So people go there thinking, oh, easy. I heard it's easy. It's not easy. You're still going up to 20,000 feet in elevation. Your body does not function at 20,000 feet in elevation because there's not as much atmosphere there. There's not as much oxygen for you to breathe. You can have all sorts of problems. Okay. Polar air versus tropical air. Okay, we're talking about wind a little bit, and this cold air mass and this hot air mass. Why do you have differences in air temperatures? Well, for one thing, the Earth's always turning, right? Always turning, so parts of it are always warm, parts of it are always cold. So you're always going to get that effect. And there's the equator versus the pole, right? We talked about 2.5 times more energy coming at the equator than at the pole. So on a large scale, you're going to get big air currents where the cold polar air flows down towards the equator, and then up it goes because it's heating up, and so you get these large global scale flows of air. Okay, and so if the Earth wasn't spinning, this would be a very consistent movement. Okay, it would be very consistent movement if the Earth wasn't spinning, but the Earth is spinning, so that's going to have an effect on how orderly this movement is. But the cold air is coming from the poles towards the equator. That's just cold air moving under the warmer air. But the spin of the Earth is definitely going to affect the wind. We're always heating up a part of it and cooling off a part of it. And then we also have uneven surface temperatures. Some parts of the Earth absorb a lot more heat than other parts. If you have a big pile of rocks, some big rocky mountain, and a lake, the lake is going to absorb the heat and change temperature much less than the rocks, right? It's clear. You can touch the water, you can touch the rock. The rock's going to be much hotter. If you are a vulture, you're going to look for these pockets of warm air. So this whole bunch of vultures here, and hawks and things, it's not that something has died right here, it's that they found a pocket of rising warm air. And they want, they've got to get up high to go looking for food. They don't want to waste their energy flapping when they can just find a thermal and circle around in that warm air and go higher and higher and higher. So vultures are very good at finding thermals. If you're in a little glider plane or a parasail or something that doesn't have an engine on it, you're also going to look for thermals and try to take advantage of the thermal to lift you up to a higher part, because that's the only way you can go up, is relying on the thermals. Once you're parasailing, let's just do a search for parasailing. Sailing. People, that's not the word I wanted. Not parasailing. Paragliding. Paragliding. You have, kind of a parachute, but you're trying to catch thermals, and which is just wind that's going up, rising wind, and you're trying to go high enough to stay. You're trying to get those thermals so you can stay in the air as long as possible. And cliffside is a good spot. Now, there's not heat coming off of the ocean, but there is wind hitting this mass and blowing up. So starting right here, jumping off the cliff right here is good, because you don't really jump off the cliff. The wind picks you up, and you can float around like this. And people have competitions. It's always, how far can you go? How long can you stay in the air? How many hours can you stay up? And that comes down to finding good thermals, pockets of air that are going up, getting up as high as you can, and then you can go along until and you're slowly going down until you find the next one to lift you up, and then down. Anyhow, this is going to cause wind too, right? So here's a hot place, here's a cool place. You're going to get some wind. So because cold air is heavier than warm air, it applies more pressure to the Earth's surface. So when we look at a map or we hear about a high pressure system, that's colder air. Winds are caused by shifting air masses due to uneven temperature. Winds always move from cold, high pressure areas towards warmer, low pressure areas. Winds are always named for the direction they come from. So if it's north to south, that's a north wind. If it's south to north, it's a south wind. So basically, the wind, cold air pushing the warmer air out of the way. Now, told you that those convection currents would be very orderly, going from the poles down to the equator, back up to the poles, down to the equator. It's less orderly because of the Coriolis effect, with the Earth spinning around. So the fact that the Earth is spinning, rotating, causes a spin, and you get deflection. You get deflection of the hemispheres. This is called the Coriolis effect. If we look at the Coriolis effect, There's a nice video explanation of it. Well, you get a lot of different videos. Coriolis Effect demonstration. You can demonstrate it on a merry-go-round. I'm not seeing a merry-go-round. This is kind of a merry-go-round. This is a very simplified merry-go-round. So we'll look at Coriolis Effect here real quickly. So it's the deflection. And so these guys are going to be throwing a ball back and forth. And the ball goes straight, but it looks like it's being deflected. Okay, so here they are. There's their rotating platform. Without it rotating, the ball just goes straight back and forth. No problem. Okay, so come on and spin, guys. Okay, with the rotation, he throws it at the guy, and they miss, right? They throw it at each other, and they miss. Now, again, the ball was actually going straight, but okay, we'll see here. So, if you were an outside observer, you'd see that that was a straight line. But you're not an outside observer from the planet. You are spinning, and the wind is not outside the planet. And so here's the camera rotating with things now, and whoa, there's a deflection there. And you can see it's opposite directions. One goes off to the right, one goes off to the left. Okay, so that's the Coriolis effect. Is that deflection? So objects, wind is deflected towards the right in the northern hemisphere, towards the left in the southern hemisphere. Turn that into a question. Which direction is wind deflected in the southern hemisphere? To the left. What's this called? Coriolis effect. Okay, and so we end up with wind belts and cells about every 30 degrees. And so the degrees, I still have that mosquito, the degrees, equator to 30 degrees, basically we have a tropical cell or Hadley cell in this area. So the cooler air coming down, up and down. So instead of coming all the way from the pole, it's chunked into about 3 sections. So we have a polar cell, mid-latitude or feral cell, and a tropical cell. And if you notice, the wind's kind of changing direction. So here it is coming down from the poles and being brought up, and so that upward motion is happening, you know, here's up, and so that forces the down to be here. And here's the tropical cell, cooler air coming down, up. It's this middle cell is going the opposite direction. The polar cell and the Hadley cell, they're going the same direction. Cooler air coming down the planet and then back up. But the mid-latitude cell, the feral cell, is actually going the opposite direction. And if you just think about the fact of, you know, where's the air rising? It's rising here and sinking here. So I don't know if that helps. But this is going to affect weather quite dramatically. At the equator, this is tropical air, lots of moisture. So it tends to go up and rain down. Because as it goes up, it cools, and it can't hold as much water as it's cooling. The water molecules condense, they fall back down. So this area, the air is going up and it's falling down. There's rain falling down pretty much every day in the tropics, right? So we have, this is a tropical forest area or whatever. There's lots of water being lifted up because there's lots of solar radiation, and so there's lots of evaporation, and then the water falls back down. most of the water has fallen back down before it reaches this point. And so by the time it gets here, it's quite dry, and there's a lot less rain at 30 degrees. So you look at 30 degrees, and you're going to tend to have deserts at 30 degrees. Let's just look at world deserts. You're going to get a belt around 30 degrees. You're going to see big Sahara Desert here, and desert here, and then 30 degrees south you get Australia, you get South Africa here, you get deserts also. Now this isn't exact, but it's a fairly big pattern that you're going to have this band of desert. Now, why isn't all of North America desert at that part, and why is, what's going on here in North America? Let me see if I can, why does it go pretty far north there? Well, this is because we have ocean here, and then we have Rocky Mountains here. And so the cool, moist air coming in from the ocean, it hits those mountains and it goes up, and as it goes up, it loses its precipitation, it loses its water. And so when it gets over the mountains, the clouds are dry. Basically, it's a sponge that's been squeezed out, so they have nothing left to give. And so we have this area that's not getting as much rain. Same thing. Well, I don't know how the winds are coming down here. I was going to say that you got Andes Mountains. It's going to affect things down in South America. Anyway, here's 30 degrees. Here's Australia. Here's 30 degrees. And if America was further down, then we'd have a big interior desert like Australia. But we just got lucky, right? So here's 30 degree line. You get massive Saharan desert and so forth. Okay, just another effect on weather, these wind belts. What's the tropical cell also called? Hadley cell. What's the mid-latitude cell also called? Ferrel cell. Okay, and then the polar cell is the polar cell. I don't think there's another name for polar cell, but it's about every 30 degrees. 30, 60, 90, right? That's as far up as you go. 90 degrees is the pole. Monsoons, seasonal winds caused by land and sea. So the air is going to cool as it goes over the ocean, warm over the land. So you get this sort of cycle going. Now as it comes in, it's picking up moisture, hits the land, goes up. Oh, now I can't hold that water, and so I drop it back down as rain. Okay, and that goes around and around. So a strong monsoon, it's going to hit in the wintertime, and these clouds can be tall and they're full of moisture, and as they get up high, they're more likely to rain. And it's going to be more likely to rain in the evening too, because things are cooling off. Those water molecules clump together more because they're slowing down, so they form rain and they fall down. In the wintertime, the land is cool, and the water tends to be the warmer, and so your monsoon season is going to be more pronounced closer to the equator, but so the winds are basically reversed, right? Basically reversed. The rain is going to happen over the ocean, which does nothing for the land. Okay, so monsoons. Some places get, and we get some monsoons, I imagine. Some heavy summer rains like we just had. Okay. Land, sea breezes, daily. This is the same thing. This is what we just talked about. So I'm not going to say it again. Mountain breezes. Okay, if you have mountains, that definitely affects things. You're going to have cool air coming down from the mountains. And so, especially Evening time, it's pleasant. If you live in the valley here, it smells really good to have this cool mountain air come down. It's nice, but if I showed you the pictures of the inversion, if that air just settles there and stays there, then it's not so nice. But then in the morning time, the air goes in the opposite direction. It tends to go up the canyons, the warm air. Okay. Review the water cycle. I'm not going to talk about it right now. Evaporation is from lakes and streams and ocean. Transpiration is what's coming out of plants. Okay. Some stuff about evaporation. And evaporation of 1 gram of water at 100 degrees Celsius requires 540 calories of heat energy. Is that an important tidbit? I don't know. That's a little confusing. I can't say whether there's a question about that or not because I didn't write the tests, but that's too gee-whizzy for me. That's too much of a tidbit to try to remember. I would rather, if you wanted to know something like that, I'd say Celsius, the term Celsius, the scale was, if you heat 1 gram of water with 1 calorie of energy, it will go up 1 degree Celsius. That's how it works. Evaporation, I don't like that tidbit, but I don't like it partly because 540 calories is not what you think it is. When you eat food, those are not calories. Technically, those are kilocalories. Those are thousands of calories. We don't like to call them kilocalories because, if your Big Mac is 400 calories or whatever it is, you don't want to think of it as being 400,000 calories, right? That's just not a nice thing. So we just call it a calorie with a big C. Technically, that's a kilocalorie. But when they talk about calories here to heat up the energy, they're talking, so 540 calories is not, a big hamburger's worth of energy for a tiny little gram of water. 540 calories is 0.54. It's half of a calorie for what you think of a calorie. So, a lifesaver candy is like 9 calories, but really it's 9,000 calories in terms of the little c calorie that they're talking about here. So a piece of, a fraction of a lifesaver of energy is enough to evaporate 1 gram of water at 100 degrees Celsius. In other words, when the water's already hot, it needs a little more energy to get actually released into the air. But I don't like those numbers as a tidbit to know personally. Okay, humidity, how much water is already found in the atmosphere. This is going to have an effect on how much more water can get into the atmosphere or how hard it is to get more water into the atmosphere. I will talk about humidity for a second because why is it that a humid day feels hotter than a dry day? Because on a dry day, when you sweat, the sweat can easily evaporate into the atmosphere. And as it evaporates, it uses that 540 calories of energy per gram of water. It uses the water, it's pulling energy out of you in the form of heat. So as it evaporates, it cools you off. And we know about evaporative cooling. It's nice to spray ourselves or mist ourselves and to feel that cooling. On a humid day, the air is already saturated with water. The sweat can't evaporate as easily. You're not going to cool off as well. So that definitely affects things. condensation is the opposite. As the air cools, it condenses. You know, if you have a glass of ice water, you'll see the water molecules condensing on the outside of the glass. That's going to happen more on a humid day than on a hot day. Condensation, you know, you see it on your car window in the morning, maybe. The dew point is the temperature at which the water in the air will condense onto something solid. So, and the dew point, you know, if it's the temperature at which the water in the air might come out as rain or dew or frost or snow, and the more water that's in the air, the easier it is for it to fall out, right? So if it's very humid, the dew point is going to be a higher temperature than if it's very dry. So, and this just changed quite dramatically between climates. So St. George, Utah, with it very dry, the dew point is going to be very low. So even in the wintertime, they're not likely to get frost on the windshield or even get condensation. It's an unusual thing that you'd have water condensed on your car window even in the wintertime. Condensation nuclei, basically what gets rain started. And little microscopic, here's a raindrop, here's a little cloud droplet. So clouds are made of these tiny little droplets, and these tiny little droplets might come together and form much bigger rain droplets. And certainly as the cloud cools off more of them will stick together and it's more likely to rain. But the water droplets need to form around a little nucleus, which is just a piece of dust that attracts the water to it. And you can seed a cloud and make it rain. You can fly over and spray dust out into the clouds and make it rain. If there's a lot of, you know, if there's quite a bit of water in that cloud but it's not raining, you can make it rain. I don't know how often this is done. Every time I look into it, I get into weird conspiracy theories about government controlling the weather and chemtrails. Anyway, it gets a little bizarre when you look up that stuff on the internet. But you can, and they do. You know, sometimes local governments decide, you know, the crops over here need the rain, we're going to go seed the clouds. But there's always some dust in the air anyway. Clouds, cloud types. Well, I'll tell you, my favorite are the cumulonimbus, because they're great, big, fluffy, and they're tall. They go clear up high, and you know, you might even get an anvil cloud and bring summer rains a lot of times. The low clouds, cumulus. Here's cumulus is starting to get higher. Stratus. I thought stratus was a little higher, but altostratus is higher. Cirrostratus is higher still. Stratus is these flat clouds. Cumulus are the more poofy clouds. And so stratus, altostratus, cirrostratus, just depending on how high up those flat clouds are. Cumulus clouds, little low poofy ones. Cumulus with development, getting a little higher. Cumulonimbus getting big and high. Altocumulus is in the middle range. Alto, think of singer, you know, that's an alto. There's lower than a soprano, but higher than the tenor. So alto's in this middle range, pretty high. Altocumulus, altostratus. High, the cirrus clouds are wispy, really high up. And there's cirrus, and there's cirrostratus, but just the cirrus clouds, high wispy clouds. Cirrocumulus, I don't know. Yeah, I don't know how exactly where you draw the line between cirrus and cirrocumulus and cirrostratus. Cirrostratus are flat, cirrus are wispy. Okay. cumulonimbus goes from low to high. I like it. Okay. Rain, snow, sleet. You know what rain is. You know what snow is. Frozen ice crystals, delicate little ice crystals falling slowly to the ground. Sleet is snow that is more, going back up into the cloud and kind of mixing with water and becoming more of an ice pellet. Kind of hail, but not quite hail. Kind of, it's not rain, it's not snow, it's kind of in between. Freezing rain, and I've never experienced an ice storm. I don't want to, but I kind of do. So raindrops fall through a freezing layer, so it's coming down as rain, but it freezes, but it's super cooled, and super cooled is kind of a cool thing. Let me just show you super cooled water. Super cooled water, it's just water, but it's below the freezing point. It should be ice, but it didn't have a nucleus, and it got below the freezing point without freezing. But as soon as it hits something, it's going to freeze. So here's some water that they put in the freezer, and now look, he hit it, he shook it, and now suddenly, boom, ice spreading. And so it was some pure water that was below the freezing point but hadn't yet frozen. So let's just see that again. It is liquid, but it's below the freezing point, and so anything that starts it, and it can be an impact, it can be, you could also put a little drop of something in there. You could put a little piece of dust in there even, but a little particle of something will start that freezing process. So same thing with freezing rain. Here it's coming down, it's rain, but it passes through this region where it drops below the freezing temperature, but it didn't freeze. And as soon as it hits the ground, boom, ice. Cool. So, that's pretty cool. Freezing rain. It just, it's terrible for driving. But here's a guy's car enclosed in ice. And so this just fell down as rain, but it froze as soon as it hit his car. So it was liquid, but as soon as it hits the car, bam, ice. So trying to lower the window that's frozen here. So yeah, I kind of want to experience it, but I never have. Okay, hail. Now this is a great place for hail, and large. Here in this case, the rain did freeze, and then it went back up and attracted more water to it, and it goes up and down a little bit. It cycles up and down in the cloud. The longer it stays in the cloud, going up and down, the bigger the hail's going to get. And so you need strong updrafts. So remember that cumulonimbus cloud, the great big tall cloud. That's going to be more cloud that's going to produce hail, because it can lift the ice way up high, or the rain. You can lift the rain droplets way up high and freeze them, and then they fall back down, but they're going back up because if you have a strong updraft. So springtime, summertime, more likely to get hail than wintertime. And I'll leave it to you to look up, hail formation or whatever. But basically, you have to have a strong air current coming in from the side and pushing it up. And the more it swirls in the cloud, the longer time it stays in the cloud, the bigger it's going to get. Eventually, it comes out, obviously. and we experienced some pretty radical hail this year, so that was exciting. Okay, weather fronts, a cold front versus a warm front. Cold front, heavy cold air pushes the warm air mass. Okay, cold front, steep boundary, and we experience this in the wintertime here. Cold front comes in from the north. The warm front, the warm air mass follows a retreating cold air mass. So in other words, the winds just change and the cold air goes away. Bye-bye cold air, and so here comes the warm following it. Not as steep. I don't know what this frontal boundary, the steep frontal boundary, what effect that has. I suspect that it means colder or more wind on a cold front coming in, stronger winds, and more of a suddenly bam, here it is cold. A cyclone, air moves inward counterclockwise, and up it goes. Okay, I've talked for a whole hour, and I'm sorry. I'm gonna try to finish here. Anticyclone is coming down and moving in a clockwise direction. This is actually a good thing. It's usually associated with warm or good weather when you get this high pressure. Okay, hurricane formation. I'm going to leave it to you guys because I really talked too long. Storm surge. A storm surge, high onshore winds on the left side of the storm. Right side of the storm in the northern hemisphere, left side in the southern hemisphere. Well, anyway, the winds pushing the waves, and then a low pressure system here. The waves just get really big. No, that's not a very good explanation. But right in the middle of a tropical cyclone, hurricane thing, is low pressure. The eye of the hurricane is low pressure, so the water tends to rise up. And so the wind pushing it towards the eye, plus the eye, you get this big wall of water, and eventually whoosh, the whole thing can come whooshing towards, and the whole cyclone's moving towards land, and so guess what? We're bringing you a present of a wall of water. As the whole storm moves towards the land, here's this wall of water that's going to come, and when it hits the shore, storm surge, and you can certainly see some great storm surges. Oops. Here's National Geographic for a minute here. Just a lot more water than normal coming onto land, right? So the whole sea, the whole level of the sea, it's 10 feet higher than normal. The whole ocean, because you have this wall of water. And so it's just the normal ocean, but closer to land. So pretty exciting. Especially if you're a weather reporter. Okay, so tornadoes. I am starting to learn a little bit about tornadoes. We're not right in Tornado Alley. We're kind of at the edge of Tornado Alley, but close enough that we occasionally get tornadoes, right? Colder, heavy air is pushed up over lower lying, warmer, lighter air. Interesting. Yeah. I don't know enough to speak well. Instruments for weather forecasting. A thermometer measures temperature. Basically, the mercury or whatever, the molecules move faster, they spread apart, they rise up. It's on a scale, so you can read it. Barometer measures air pressure. and there are a couple options. It can be mercury again, with atmospheric pressure pushing it up higher. And this is actually the old style. This is how it's measured, is in millimeters of mercury or inches of mercury. How high up the little tube, the little vacuum tube, will the mercury rise based on the pressure. And barometer and altimeter are basically the same thing. This aneroid barometer is the other style, where the walls are actually getting squozen and there's a little spindle and lever and it changes the pointer. But so yeah, if you just have a barometer hanging in your house, and the pressure starts to drop, a low pressure system, then you say, oh, maybe bad weather's coming. And so it will, if you look at a home barometer, you'll typically get something like this, or it's going to have someplace on here a scale. Here it's in millimeters, and you can see that this drop in pressure, a lower pressure system is more likely to give you storm, higher pressure more likely to give you sun. Okay, so can't you just go look outside? Well, this will tell you a little bit ahead of time. So usually you have two needles, one that you can move and the other just moves by itself. And so you move this, yesterday you moved this to where the needle was and it was here, and then you wake up and you see that it's swung clear over to here. Well, that's a good sign, because you can say, oh, it's going to be, good weather's coming. You put the needle here yesterday or a couple hours ago or whatever, and now you see it's dropped, and you're like, ooh, the pressure's dropping. And if it drops pretty quickly, you can say, oh, a storm is coming. So it just, this change in pressure can give you a little heads up. Now, how is this also an altimeter? Well, a barometer is one that you just stick on your wall. But as you go up in elevation, you're also going to get less pressure. And so instead of putting little weather predictions on here, you just adjust it for the altitude. So an altimeter, the plain altimeter is a little different. But, well, not really. It's still measuring pressure difference. I'm thinking of more like one you would wear on your wrist. Let me specify that. Wrist altimeter. Something like that. Anyway, it's the same idea. It's just measuring pressure, and you do have to calibrate it because the weather will affect it. The weather will affect your barometer or your altimeter. So I remember hearing about this explorer. I was on a mountain in Mexico, and it was pretty far from the ocean. And you could see the ocean, but you're up on this little mountain peak. And an early explorer who wanted to know how high up he was, he climbed the mountain and he took his altimeter reading, but he didn't know if it was calibrated for that day's weather, and so he very quickly ran down the mountain and down over to the ocean, because so he could calibrate it, right? Because at the ocean, he knows this is sea level, and so then he can turn his dial. It says, I know this is 0, at sea level. Now I can calculate how high my mountain really was. Okay. So wind vane just turns to show the direction of the wind. Okay, pretty simple. It's usually a wind sock, at an airport, and that's pretty important to gauge how fast the wind is blowing, which direction it's blowing. That's pretty important if you're going to land your plane. Ducks flying into decoys. ducks coming into decoys, they're going to fly, they're going to land coming into the wind. So, you know, if it's a windy day, it's going to affect how you set out your decoys and which way the birds are going to come in. So, anyway, an anemometer, I think is how you say it, measures the wind speed, and you can make a little anemometer at home in your classroom. There's some directions in the book. Hygrometer measures the relative humidity. Psychrometer, sling psychrometer, and hair hygrometer. Sorry, I didn't read up on those. I can't tell you. What is the difference between a psychrometer, a sling psychrometer, and a hair hygrometer? Seems like a fair question. I don't know the answer. Brain gauge, you measure the amount of rainfall, or a measuring stick for snowfall, but snow is much fluffier than rain. So it's about 10 inches of snow is equivalent to 1 inch of rain. It's it's an inch of actual precipitation, actual water. There are ground stations all over the country, gathering weather data, trying to help us predict the weather, trying to give us warnings of bad weather coming. They're putting out weather balloons all the time, radiosonde, lifted high into the atmosphere, and a 90,000 foot balloon will pop, and the radiosonde parachutes back to the Earth for reuse. So they release these all the time. Hundreds of them released every day at the same time worldwide. So that's pretty cool. If you want to play with balloons, you could work in meteorology releasing these radiosones. And now they use biodegradable balloons because they're releasing them all the time. A drop sonde is dropped instead of going up in a balloon to 90,000 feet, it's dropped from an airplane, and they'll drop these as into hurricanes, for example. Weather satellites orbiting the Earth all the time. There's polar orbiting ones that are in low orbit at 500 miles, geostationary ones that stay in a certain place relative to the planet. They're 22,000 miles up approximately. So yeah, geostationary, it's rotating with the Earth. It's in motion to stay above a certain place all the time. Anyway, we have a whole network of satellites, right? And satellites are taking data on the clouds and the radiation, and you can help predict the weather. And of course, we talked about seasons already, so I'm not going to say that again. Over an hour. This was meant to be brief. Sorry, guys. Hopefully, something helpful there. Turn your reading into questions. Good luck. Sorry that I don't know the subject too well. Hope you do well tonight, and I'll talk to you soon. I'm going to see some of you tonight at 5. Bye.